Determinant of a square matrix A with entries from F denoted det A, deta, determinant A, is some function that maps A to a value in F. Okay. What is that function? The function is defined as follows. Okay, it's a precise function. It's not any function. No, it's a very precisely defined function. The function is defined as follows. For a 1 by 1 matrix, okay, 1 by 1 matrix is so trivial, right? So capital A equals just A. Determinant is equal to the value itself. Okay, easy to define. Okay, so we define sort of like a base case, which is 1 by 1. Then I'll define the n by n. Okay, this is how I'm going to define n by n. To define n by n, I need this notion of a cofactor type thing. Okay, so this is called this is one particular minor or cofactor. Okay, so this a tilde 1j, meaning a, I will get rid of the first row and the jth column. Okay, so this is the n minus 1 by n minus 1 matrix obtained by deleting row 1 and column j from A. Okay, so for instance, if j is 1, a tilde 1 1 is this matrix. You take this matrix, delete the first column, delete the first row. You will have a n minus 1 by n minus 1 matrix, right? That is this a tilde 1j. Okay, this is sort of like a minor of this matrix. These things are called minors. Okay, when you delete one row and one column, what you have left is called the minor. Okay, likewise, I can delete the first row and the first column, first row and the third column, second column, third column, fourth column, like that. I can keep deleting to get different minors. Okay, determinant of A is basically A11, the value that is here, times the determinant of this n minus 1 by n minus 1 matrix, A tilde 1 1, and then minus A12 times determinant of A tilde 1 2. Okay, so you take each of these minors, find their determinants, and then multiply by A11 times this, minus A12 times this, plus A13 times this, minus, plus, so on till the last guy will be minus 1 power n plus 1 A1n. Okay, determinant A tilde 1n, the last guy. Okay, the coefficient I am multiplying by is minus 1 power n plus 1, right? Depends on whether it's odd or even. Okay, if it is even, it will be minus. If it is odd, it will be plus. Okay, that's how it will end here. Okay, you can see that's the pattern here. Okay, simple recursive definition, right? How will I find the determinant of these guys? That goes to n minus 1 by n minus 1. And then you go to n minus 2 by n minus 2 all the way till 1. When you get 1, you just simply use the same value. Okay, so it's a recursive definition. It looks complicated. So what I'm going to do is I'm going to show you how this recursion works out for small values of n, and you'll see it's very simple. Okay, so first let's see 2 by 2 and 3 by 3, and then more cases we'll generalize. 2 by 2, a tilde 1 1 is just d, right? First column, first row removed, it's only d. A tilde 1 2 is only c, right? This and this are removed, it's only c. What is determinant A? It is a times determinant of a tilde 1 1 minus b times determinant of a tilde 1 2. Now this determinant is just d, it's 1 by 1, right? So it's ad minus bc, that's determinant of A when it's 2 by 2. A lot of people remember this formula also. For 2 by 2, determinant is ad minus bc. Okay, it's a useful formula to remember. Okay, here is a 3 by 3 matrix. How do we use this again? It's very simple. You find a tilde 1 1, it's EH Fi, a tilde 1 2, it's DG Fi, a tilde 1 3, it's DG EH. So there are 3 different minors for this matrix A. Okay, what's going to be my determinant? Determinant A is A times determinant of this minor minus B times determinant of this minor plus C times determinant of this minor. Right, that's what you have. So now determinant of this, I know from my 2 by 2, it's going to be EI minus FH. Determinant of this is DI minus FG. Determinant of this is DH minus EG. You put that in, you will get this kind of a expression. Okay, people don't usually mug up this 3 by 3 determinant. Some people do, usually people don't. You can just remember the 2 by 2 and the expansion with respect to the first one. This term is easy to come up with, right? You can come up with this very easily. So you can come up with that. Okay. So you can do similarly for any n. You can go to 4 by 4 and remember this and then go through and do it. Okay. But usually by hand people stop at 3 by 3. Beyond this is a bit of a pain. Beyond this, maybe you can use some computer program. Okay. So that's the method for generally using the definition of the determinant. Okay. What's the big deal with determinant? It has got a lot of interesting properties. Okay. Many properties. We won't see all of them. We'll only see what is needed for it. First of all, terms in the expansion. There seem to be a lot of terms in the expansion, right? Determinant A has 6 terms. Determinant A here 2 by 2 has only 2 terms, like that. Okay. It turns out determinant A has n factorial terms in the expansion. Okay, so 3 factorial is 6, right? So it has 3. 4, if you want to do 4 factorial, will be 24. Okay, there will be 24 terms in 4. Okay, in general, for n terms, n by n matrix, determinant will have n factorial terms in the expansion. Okay, so every term, okay, one of these terms is a product of the diagonal elements. All the diagonal elements multiplied, it will appear positive. All the diagonal elements multiplied will be one term. All other terms, okay, every other term of these n factorial terms, it will have at least one from the upper triangular part and at least one from the lower triangular part. Okay, you can see why that is true, the way the product works, it has to be, only one term will be all the diagonals. Anything else may involve the diagonal, but it will also involve one thing in the upper triangular part, another in the lower triangular part. Now this gives us a wonderful, wonderful property. It says determinant of the diagonal matrix is simply product of the diagonal elements, right? Easy, easy to see, because one term is the product of diagonals, that will be the only non-zero term. Every other term will go off to 0. Okay, same thing follows for an upper or lower triangular matrix. Remember, upper triangular means diagonal and everything above it can be non-zero, everything below it is 0. Likewise for lower triangular. So any lower triangular or upper triangular matrix also, determinant will be product of diagonal elements, because only that term will survive. All the other terms will go off to 0 because they involve either an upper triangular part or a lower triangular part. Okay, so this is terms in the expansion, useful property. Another very, very, very useful property in our context is determinant A becomes 0 if and only if A is singular. Okay, only when rank of A is less than n, right? So that is the same as A being singular, right? Null space of A has some non-zero vector, rank of A is less than n, nullity of A is greater than or equal to 1. So that's all conditions for A being singular. So that makes determinant A 0, and otherwise it's non-zero. Okay, why is this true? I mean, there's ways to prove it. We will not prove it in this class. The intuition is basically absolute value of determinant of A is some sort of a volume of an n-dimensional figure, n-dimensional parallelepiped formed by rows of A. Okay, what is this? All this, I'm not going to go into details. It is basically determinant of A is an n-dimensional volume. Now, if the rows of A are linearly dependent, then you don't have n dimensions, right? You're going to go less than n dimension, then volume goes to 0. Okay, area, only if there are 2 dimensions you have area. If you have only 1 dimension along a line, area is 0. Like that, when you go to less than n dimensions, volume will go to 0, so determinant A goes to 0. It's the only way it can happen. There are also other rigorous ways to prove this in different ways, but we won't prove it here. We'll accept it as a fact, and this will be a very, very useful fact for us. Okay. Another very useful fact for us is determinant is very well behaved with product. Determinant AB is equal to determinant A times determinant B. Okay, so determinant AB is determinant A plus determinant B, but determinant A plus B is not determinant A plus determinant B. Okay, it doesn't behave like that with some. It's a much more complicated thing there. But determinant AB is determinant A into determinant B. With product, it's very well behaved. Okay.